Section 14.1 is an introduction to finding a limit. All right, and limits are crucial in the study of calculus. So this will help get you a leg up when moving from pre-calculus to calculus. So in 14.1, we're going to look at finding limits using tables and graphs. All right, in 14.2, we will algebraically calculate the value of a limit. So we have this limit statement here. So it's the limit as x approaches a of a function equals L. Right? And so I'm going to write a formal definition here. So the limit of f of x as x approaches a is L. So that's exactly how we would read this, right? The limit of f of x as x approaches a equals L. So when we evaluate a limit, you see this word approach, right? The word approach means you get near a, but you don't equal a, right? So and when we get near a, we're talking on both sides of a, right? So we're going to look at x values greater than a and x values less than a. And so when we plug those numbers into our function, we're going to see if the function is approaching some number L. All right, so we're going to choose x values close to a. On both sides of a, but not a itself. And we're going to see if the function is getting close to some number L, right? And see getting close to a number L, right? So I have 3 examples here, and each of these examples, the limit will exist, all right? So I have this function here. Here's my function. It's increasing. And we're going to look at the limit as x approaches a of this function. Now this is a nice seamless line, right? And you can kind of see that f of a has a point on the graph, and that point is at L. So when we choose, we're going to choose x values approaching a, so closing in on a. And so we're going to get really close. We're not going to start far away. I like to start within a tenth, okay, and move in. So really close to a. If I were to plug in values greater than a, my function values would decrease to this number L. And if I were to pick x values less than a and plug those numbers into the function or look at the graph, the function values are going to increase to a number L. And so because the function values are approaching the same number, right, on the right-hand side and on the left-hand side, this limit is going to equal L. On the next example, you'll notice we have the same increasing function. We have the a value here and the L value here, but this function has a hole in it. And at that hole, they've kind of removed this point and they've plotted it somewhere else, right? So when we look at the limit as x approaches a of this function, remember we're going to choose x values near a, but not where it equals a, All right. So again, if I were to choose x values in some interval greater than a, those function values would be approaching L. They're approaching this whole. And if I were to choose x values less than a, the function values would increase to this number L. So because the function values are both, on both sides, are approaching the same number, we say that this limit is L. And this is kind of tricky for some people, right? It's not what the function is doing at a, it's what the function is doing as x is approaching a, right? Approaching, not equaling. So we're going to look on both sides, approaching on both sides. And approaching on both sides, we're approaching this whole, right? Because it's approaching the same number, and the function values are approaching the same number, we're going to say this limit still equals L. Now, the limit is different than the function value. So if I asked, or if you were asked, what is f of a? Okay, f of a is not L, right? The function value at a is not where the whole is. The function value is up here where the point is. So let me just call it m for now, all right? So the function value at a is actually m, where the limit is L. Okay, so the limit is where the lines are going, and the function value is where those defined points are. All right, so here on the third example, okay, the same function, this one has a hole, right? And this hole, this point was not plotted anywhere, right? So I want you to realize that the function at a does not exist, right? The function value doesn't exist. But if we were to investigate what the limit of this function was, right? And again, we're approaching a, we're not equaling a. So if we let our x values approach a on the right-hand side, those function values are going to decrease to L. If we let our x values approach a on the left-hand side, those function values are going to increase to the number L. So we say that this limit is still L, right? So whether it's defined elsewhere, or not defined, if your graph, okay, if your lines are approaching the same function value, the limit will exist. All right. So when does a limit not exist? All right. Just for example, let's say here's a, and let's say we had something like so. Okay. And so if we were to look at the limit as x approaches a of this function, if we picked values greater than a, and I were to plug those function values, let me call this L, and let me call this M, okay? So if we were to pick x values greater than a and plug those into the function values are on this line here on the right. And so if I get closer and closer to a, those function values are approaching this number m, right? And so if I were to pick x values less than a and plug them into the function, these function values are getting closer and closer and closer to L. So because there's a gap here, because when we pick x values less than a, we're getting L, and when we pick values greater than a, we're getting values getting closer to m, we say this limit does not exist, right? So it's got to approach the same number on the left and the right. Another instance of where a function does not exist is if there was an asymptote. Right? So if we were to look at the limit as x approaches a of this function, the closer we get to a, the faster these function values are growing, right? And so because we can't equal infinity, we say this limit does not exist. Now, in some cases, in some instances, we will write infinity here, but technically, this limit does not exist because you can't let a limit equal infinity, all right? So graphically, this is what we're going to do, right? We're going to pick x values on an interval greater than a and less than a and see if those function values are approaching the same number. Right? Remember, they have to approach the same number on the right-hand side and the left-hand side. Using a table, I like to use the calculator quite a bit. All right, so I'm going to show you how to use a table to evaluate a limit. Oops, tables. All right, so let's look at the limit as x approaches 3 of this function. So I'm going to build this horizontal table here. Right? So we're evaluating the limit as x approaches 3. So I'm going to put 3 here in the middle. Okay. And then we need to pick values greater than 3 and values less than 3. And I say it before, I like to stay within a tenth. All right. So if I were to pick values greater than 3, the furthest away I'm going to go is 3.1. Right? So when we say approaching, we're talking like microscopic distance away from 3. Right? So then I want to get closer to 3 than 3.1. And so I'm just going to start adding zeros here. This is 1/10 away. So I'm going to do 3.01, which is 1/100th away. And then I'm going to do 3.001, which is 1,000th away from 3. And so you can see that we're approaching 3 from the right-hand side. Right, so I'm going to do the same, but less than 3. So 1/10 away from 3 is 2.9. If I wanted to get 100th away from 3, I'm just going to start adding 9. So 2.99 is 100th less than 3. And then I'm going to get one factor closer to 3 by adding another 9, 2.999. This is 1,000th away from 3. And so what I'm going to do is I'm going to plug these decimals into the function. Right? So I like to use the calculator to do this because it's much faster. And so in order to use the calculator, we're going to use the table feature. Right? So on your calculator, make sure your table is set up to ask. So second window will get you your table setup menu. Now it's not necessarily important where the table start or the change in table is, but if you wanted to zero that out, that's kind of standard there. But what is important is that the independent variable is set to ask, and the dependent variable is still at auto. Okay, so this is going to allow us to custom build our table and put in whatever x values we want to. Right? So in order to use the table now, we have to have a function in our y equals. So y equals, go ahead and plug the function that we're taking the limit of. So parentheses x squared minus 9, close parentheses, divided by parentheses x squared minus 3x, close those parentheses. Now we have our function in our calculator. So I'm going to go to the table and I'm going to plug these values in there. So in the table, remember, if there's numbers there, you just type over them. So I'm just going to plug in 2.9, 2.99, 2.999, 3, 3.001, 3.01, 3.1. Okay. So really quickly, I just plugged in all of these values, and so I'm going to copy these decimals into my table. All right, so here we go. Now, at the end of a table, to evaluate a limit, it's almost always a guess. All right, so you have to ask yourself, did you pick values of x close enough to 3 to accurately guess where this function is heading, right? So when we picked values less than 3, we got 2.03, 2.003, 2.0003, and I'll wager that if we were to add 9s, we'd still just keep adding zeros here. So it looks like these function values are decreasing to 2, right? That would be a reasonable guess, that the function values started greater than 2, but they're heading down to 2, right? Now on the right-hand side, we went from 1.96 to 1.996 to 1.9997. And so it looks like these function values, the closer we get to 3, the function values are increasing to 2. And now notice what happens at 3. We're getting an error, right? But the limit doesn't care what the function is doing when x equals 3, just what it's doing when it's approaching 3. So it looks like on the right-hand side, we're increasing to 2. On the left-hand side, we're decreasing to 2. And so we're going to guess, okay, accurately guess, it is an educated guess, that this limit is indeed going to be 2. Now, if you can't logically conclude that this is going to 2, just add a 9 and add a 0 and get one step closer. Get 1/10,000th away from 3 and see if you can accurately guess, all right? But that's how we're going to use a table, right? So this graph right here has a hole in it. That's what this means, that there's an error here. It's going to decrease and increase to the same number, but at that number, it's going to have a hole, right? So I would like to do just a few more with you, right? One more regular function, and then I'd like to look at some piecewise functions here. So let's do x approaching 0 of e to the x plus 1. So we're letting our x values approach 0, and we want to find the limits of e to the x plus 1. So I'm going to build the table again. And since the limit is approaching 0, I'm going to put 0 in the middle. Now on the right, I want to pick numbers greater than 0, but still stay within a 10th, a 100th, a 1,000th, possibly 10,000ths. Right? So a 10th is 0.1, a 100th is 0.01, a 1,000th is 0.001, and since I have space, I'm going to go ahead and go 1/10,000th away, 0.0001. Right? So we're just adding zeros in front of the 1 to get closer to 0. Now on the negative side, if a 10th away from 0 is negative 0.1, right? And if I want to get 100th away from 0, if I subtract 100th from 0, I'm going to get negative 0.01, right? Because we want it to approach 0, right? 0.99, negative 0.9 is close to negative 1, just FYI. So when we go on the negative side here, we're doing 0 minus 100th. Okay, 0 minus 1,000th is negative 0.001, right? Because we're 1,000th away. And then one more, squeeze it in here, 1/10,000th away from 0. So I want to plug these values into the calculator in order to fill out this table. So I'm going to go to my y equals and change out the function first. Now I want e to the x plus 1. Oops. Let's try that again. E to the x plus 1. Okay, that looks better. All right, and then I want to go to the table, and I'm going to change out these values for my new x values. So negative 0.1, negative 0.01, negative 0.001, 0.0001, 0, 0.0001, 0.001, 0.01, and finally 0.1. Okay, so really quickly, right, we can get these decimals. Now, if you ever need more decimal places, remember you can use your cursor here and scroll over and highlight that y value, and down here on the input line it gives you 9 to 10 places, okay, decimal places. So if the table is just rounding it to 4 places at all times. But if you wanted to get more decimal places, you could just highlight it, right? So sometimes the computer asks for more than 4 decimal places, and so this would be how you can find that, right? But I'm going to go ahead and write down 4 decimal places is usually good for guessing the value of a limit. All right, so I got the same value. Oh, I put 0.01 in there again instead of 0.1. So let me fix this one. 2.1052. Okay, so here we go, right? Now on this table, when we plugged 0 in, we actually did get 2. Right, so this function doesn't have a hole. It is actually defined. It's one of those first examples, right? It's this one, okay, where the function is nice and defined and smooth, okay? The previous one, we had a hole in there. But notice that the limits are going to be the same, right? But we still want to not focus on this point here. We just want to focus on what it's doing near 0, right? So on the greater than side, when we pick values greater than 0, plug them in, we're decreasing to 2, right? We start at 2.1 and then we slowly decrease to 2. If we pick values less than 0, we're increasing to 2. We start at 1.9048 and then we just started adding 9s, right? So 1.9999, I think it's a reasonable guess that this is approaching 2. 2.0001, I think it's reasonable to round this to 2. And just as an added clarification, right, when we plug 0 in there, we're going to get 2. So we're going to guess this limit, okay, an educated guess that this limit is indeed 2. All right, so this is how you would build tables up, okay, and evaluate those limits. So let's look at a piecewise defined function. All right, so we have this piecewise defined function here. The limit of a function as x approaches 0, okay, but the function is 2 different functions depending on which side of 0 you're at, right? Now we're still going to build a table here and guess the value of our limit at the end of this table, right? So I am going to plug 0 in the middle, because we're looking at the limit as x approaches 0. And I'm still going to pick the same values as I did before. Okay, so I'm going to start a 10th away and move closer to 100th away, closer to 1,000th away, and even closer yet to 1/10,000th away. And the same thing on the other side, 100th away, 1/10th away, then 100th, then 1,000th, and then 1/10,000th. Right? And I'm going to plug those numbers into the function. Right? Now, we have two different functions to utilize here, right? So this says if x is less than 0, we're to use this function. So less than 0 is this part of our table, right? And so for these 4 values, I'm going to use the x minus 1 function. Okay, and then if x is greater than or equal to 0, I'm going to use this function. So for the remainder of my table, I'm going to use the 3x minus 1 function. So we have to plug these x values into 2 different functions because we have this piecewise defined function above. And so first I'm going to do the x minus 1 function. All right, and I'm going to plug these values in. Now what's kind of nice about doing a bunch of limits at 0 is that our table is going to already have those x values plugged in. Okay, so I'm not going to plug in the 0 one. I'm just going to plug in the first 4 here. So negative 1.1, negative 1.01, negative 1.001, and then at negative 1, e to the negative 4, right? Remember, this is a 1 with 4 decimal places in front of it, so that puts it accurate to this decimal. It just says it's equal to negative 1. But if you were to scroll over, you would see the true decimal, right? So the calculator, because there's too many decimal places in there, it just rounded it to negative 1. But I'm going to put the true decimal in there, which is a negative 1 followed by 3 zeros and a 1. Okay. Now, that's those 4 values. So when I do the next part of the table, I've got to make sure I'm plugging it into the correct function. So I'm going to go change my y equals out to 3x minus 1 now. And then I'm going to do the table. And I'm going to look at not the first 4 values, but, starting at 0. So again, starting at 0, I'm going to go ahead and highlight that over there. So at 0, it is a true negative 1, right? I highlighted it. There is no decimal places. Excuse me. Now at 0.0001, the table shows it's negative 1, but when I highlight it, I get negative 0.9997. Okay, so I'm going to use those decimals there. This one is negative 0.997, negative 0.97, excuse me, and negative 0.7. All right, so can we logically conclude that this function is heading to the same value, greater than 0 and less than 0? So we don't care what this middle number is here. But if the less than 0, all these numbers are approaching negative 1, right? We're getting closer and closer to negative 1. Greater than 0, these numbers are also approaching negative 1. So at the end of this table, I would guess, logically guess, that the value of the limit is indeed negative 1. Okay. So let's do one more piecewise defined function here. The function, or the limit, as x approaches 2 of a function All right, so we're evaluating the limit as x approaches 2 this time of our function. And notice that our function is 2 different functions on either side of 2. All right, so we have to make sure when we fill out our table, we're using the correct function. So I'm going to build this horizontal table. And since the limit is approaching 2, I'm going to put 2 in the middle here, right? And then I'm going to pick my x values. Okay, greater than 2. 1/10 greater than 2 is 2.1. 100th, 2.01. 1,000th, 2.001. And I think that's going to be good enough. I have a little space here, but I'm not going to worry about it. 1/10 less than 2 is at 1.9. 100th less than 2 is 1.99. And 1,000th less than 2 is 1.999. Okay. So these are the values that I want to plug into the function. Now, which function are we going to use, right? Look at the indicated domains. If x is less than or equal to 2, we want to use x squared. So less than or equal to 2 is the first 4 numbers here on my function. I'm going to use x squared when I plug those into the table. If x is greater than 2, we're going to use this other function. So that's the last 3 values on this table. We're going to use this function. Okay. So let's go ahead and do that. First, let's do the less than side. So y equals, plug x squared in there, and then change those table values out. Sorry guys, I got a tickle in my throat. Alright, so it looks like I have 3.61, 3.9601, 3.996, and 4. Okay, so then when I fill out this other table, I need to make sure I'm switching out the y equals. And I'm going to plug in 2.001, 2.01, and 2.1. Okay, so it looks like when we picked values greater than 2, we started at 3.2 and we're slowly adding zeros and getting closer to 3, right? These values are approaching 3. If we look at the values less than 2, these values are starting at 3.6, but they're not decreasing, right? They're increasing, and they're slowly getting closer and closer to 4. So because, again, and we don't care what this function is doing here, okay? We plug it in. I usually plug it in, but it actually doesn't matter when we evaluate the limit. So the function values on the left, these values are going up to 4. The function values on the right, these values are going down to 3. So because they're not approaching the same number, we would say that this limit does not exist. All right, so the guess limit does not exist. All right, so it doesn't matter that these values are approaching the same as the function value. It doesn't matter that this is, approaching the true function value at 2, because when we evaluate a limit, it doesn't matter what the function is doing at 2, just what it's doing near 2. All right? So I have some graphs here that I would like to evaluate the limit of. Pardon me while I scratch out the answers. Here we go. So let's look at evaluating some more limits graphically. Right. So on number 17, we're looking at the limit as x approaches 2. So x is approaching 2 here, right? And so if I pick values greater than 2, we're on this upward curve here. And if I pick values less than 2, we're on this upward curve here. But all those function values are increasing to the same number, right? It's increasing to the same point. And so the value of the limit is the y value, right? X is where we're looking. The y value is where we're landing. So the function value is the value of the limit. So we're going to get an answer of 3 here because the function values are increasing to 3 on both sides. Right, number 18. We're doing the limit as x approaches 4. So we're going to look on the x-axis at 4, and then we're going to pick values greater than 4 and less than 4 and see what the function is doing. Right, so greater than 4, we're going to be decreasing till we get to -3. Less than 4, we're also going to be decreasing until we get to a function value of -3. So because both sides, on the left and the right, they're approaching the same number, the limit value is the function value, right? The y value, -3. Number 19, what's the limit of this function as x approaches 2, right? So we're getting close to 2, but not where it equals 2. So notice this one has a hole at 2, and it's defined to be here. But if we just get close to 2, on both sides and ignore what it's doing at 2, both on the greater than 2, we're increasing to 4. Less than 2, we're increasing to 4. At 2, we have a hole, but that doesn't matter when we evaluate the limit. So we're going to say this limit is 4. Okay. Same thing here. The limit as x approaches 2. This graph has a hole in it. And that point is removed and plotted somewhere else. But when we evaluate the limit, it doesn't matter where the point is. It matters what the graph is doing near 2. Right? So greater than 2, these function values are decreasing to 2. Less than 2, x values, the function values are increasing to 2. So because they're approaching the same number, we say that this limit is indeed 2. Right? Number 21 here, the limit as x approaches 3. If we were to pick values greater than 3 and plug those into the function, we're going to be on this line, right? And the closer we get to x equals 3, this line is heading up to 6, right? If we were to pick values less than 3, we're going to be on this curve. And so the closer we get to 3 on the left-hand side, this curve is approaching a function value of 3. So because the right-hand side is going to 6 and the left-hand side is going to 3, we say that this value of the limit does not exist. All right? They have to be approaching the same number in order for the limit to exist. So what do you say about 4? Right? If you pick x values greater than 4, you're going to be on this line. And this line is decreasing to 2. If you pick x values less than 4 and plug them into the function is going to be on this curve. And this curve is decreasing to 4. So because on the left-hand side, it's not approaching the same number as the right-hand side, again, we would say this limit does not exist. Right, so practice those. Make sure you can evaluate a limit using a table and using the graph.